So what is an item? An item is a production, or an LR0 item is a production with a dot somewhere on the right. Okay? So what the dot says is, this is where I currently am. So the dot could be anywhere on the right. It could be all the way over on the left of the right-hand side, all the way at the beginning of the right-hand side. It could be one over, it could be here, it could be all the way at the end. The various places where I could put the dot. So you think of taking the right-hand side, the sequence of symbols, and just dividing it up into two. So what the dot does is divides the right-hand side of a production into some part here and some part here. And I can do that in many different ways. So the intuition of an item is that when I have an item A goes to alpha dot beta, what this denotes is that in the current state of the parser, this item says that the parser has seen something that could be derived from alpha, and therefore that one possibility in terms of the rest of the input, one possibility is that it might see something derivable from beta. Okay? So if I have an item A goes to alpha dot beta, this effectively divides up the right-hand side, A goes to alpha beta, divides it up into two parts. One part is what the parser has seen already, and one is what it might see. Okay, that would be a legal continuation. So it would be legal to see something derivable from beta at this point. If you look at your y dot output states, each state has a whole bunch of things that look like this. You have production, left-hand side goes to stuff dot stuff. That's what those guys are. Actually, the states in your y dot output are a little bit more than this, because the parsers that Yak produces don't use LR0 items, they use LR1 items, but the intuition is exactly the same. You have an item with something dot something. This is what I have seen already. This is what I could see. So the general approach is, if I give you a grammar G with a start symbol S, what I'm going to do first is construct an augmented grammar. So I'm going to throw in a new start symbol S prime, and a new production S prime goes to S. This is just for convenience, okay? Because sometimes the start symbol can be recursive. Okay, so for example, in the C++ grammar, the start symbol is recursive. It says a program can be a function or a prototype or declarations or whatever, followed by more program. So there's recursion there. And this, introducing a new non-terminal, new start symbol, essentially takes the recursion out, and it simplifies some processing down the road. So now I've introduced this new non-terminal. So let's think of the intuition about the state in which the parser starts out. An item, A goes to alpha dot beta, means that this corresponds to a parser state, actually a component of a parser state, where the parser has seen something that alpha could derive. That's already seen. And it looks to see something that beta could derive as a possible continuation. So the start state of my parser automaton, in its very initial state, if you think of the parser's very initial state, the parser has not seen anything at all, hasn't looked at the input yet because it's just beginning, and it's looking to see something that could be derived from the original start symbol. Does that seem reasonable? At the very beginning, it hasn't seen anything, and it's looking to see something that you could derive from the original start symbol, because that would be a valid program. So that's why the initial state of the parser corresponds to an LR0 item. S prime goes to dot S, because it hasn't seen anything, and it's looking to see something that you could get from S. Okay? And then so what we'll do is we'll construct a finite state automaton starting with this LR0 item and doing some processing, some magic that we'll now talk about. And then we'll take this automaton and we'll construct the parse table based on this automaton. So that's the game plan. That's how we are going to be doing it. What I'm going to do is I'm going to begin by describing how to construct an NFA, a non-deterministic automaton, because that turns out to be simpler in some ways. And then we'll go from the non-deterministic thing to a deterministic automaton. Okay, and that's what will give us the parse table. Okay, so in the non-deterministic automaton, each state is going to be labeled by one LR0 item. Okay? The initial state is labeled by S prime goes to dot S. So we've talked about that initial state already. Here are the transitions. If I have a state that's labeled with A goes to alpha dot X beta, then I can make a transition on grammar symbol X, and I can go to a state that's labeled with A goes to alpha X dot beta. So let's think about what this is trying to express. Okay? This is a state where the parser has seen something that alpha could derive, and it's looking to see something. So one possible continuation for the input would be something that X beta could derive. Right? Now, suppose it sees something that is derivable from X. So again, these are context-free grammars. Because it's a context-free grammar, anything that is derivable from X beta is a string where there's a first part that's derivable from X, and there's a second part that's derivable from beta. That's because it's context-free. So if I'm looking to see something that X beta could derive, and I see something that X derives, then I can move to a state where I've seen something that alpha X could derive, and I'm looking for something that beta can derive. Does that make sense? Amr. The alpha X and beta have to be contiguous in the input string. Yes, they have to be. But I want to point this out. Alpha X and beta, so alpha and beta can be some sequence of grammar symbols. So it could be a whole bunch of symbols. They could be tokens and non-terminals or variables. And here's where things are different than ordinary finite state automata. X can be either a terminal or a non-terminal. So remember, terminal is another word for token. Non-terminal is another word for variable. If I'm using a standard finite state automaton, the transitions are only on symbols that are in the input alphabet, right? For an ordinary finite state machine. So in this case, if this were an ordinary finite state machine, the transitions would only be on, I don't know, what's the input alphabet here? It's tokens. So if this were an ordinary finite state machine, the transitions would be only on tokens. But we know that doing transitions only on tokens and using only an ordinary finite state machine would not be enough, because context-free grammars are strictly more powerful than regular languages, regular expressions. They're strictly more expressive. So there are things that you can say with context-free grammars that you cannot say using regular expressions. So turn that around. There are input strings derivable from context-free grammars that you cannot parse using ordinary finite state machines. So in this case, X can be either a terminal or a variable. What are some of the variables that you guys saw in your HTML parser? HTML in angle brackets? The non-terminal, the variable HTML. Yeah, good. Some others? Item, that's right. List, so on, right? So, what's that? List item. I've forgotten what that is. So, in the case of C++ or C or Java or something, expression might be a non-terminal, or statement, or function. So this now, if it's a non-terminal, that means that it potentially matches many, many different possible input tokens, input token sequences. So for example, if I have a production that says expression goes to expression plus expression, so this is in the calculator example that you guys have discussed. So now that each of those expressions potentially matches many different input sequences, right? So I'm making I'm allowing my variable prefix automaton to make transitions on variables, which means that potentially this transition could refer to many different possible input sequences, input token sequences. But the essential intuition I want you to take away from this is that in this state, I've seen something that alpha could derive. I'm looking at something x beta could derive as a possible continuation. Then I see something that x could derive. So now I can move to a state where I've seen something that alpha x can derive, and a possible continuation is something from beta. Just now I was talking about x being a variable, like expression or function or HTML. And that matches many different possible input tokens. What if x is a token, like list begin or bold begin, or I've forgotten what what those were in HTML, or identifier or integer constant. What if this is a token? Then what? What does it mean to say something that x could derive? Suppose x is integer constant. What can x derive? What's that, Dakota? It derives x itself. Any token, well, let's think of go back to the notion of derivation. What's the definition of a derivation step? I have some sequence of grammar symbols, and then what happens? I apply 0 or more rules to get the other guy. So let's actually write that down. This is worth going through. So let's say I have something alpha, something beta. This is one derivation step, okay? Some number of derivation steps. So what's the relationship between this and this? What have I done in this process? You were saying it. Tell me again. I apply 0 or more. Okay. I apply 0 more productions to get beta. Okay, what does applying a production mean? Someone else. What's that? Translated? Yes, translated, but you'll have to be more specific. What am I doing?
Reducing it to
That's the intuition is correct, but tell me more mechanistically. What exactly am I doing? I'm taking a left-hand side of a rule and doing what? Replacing it with the right-hand side. And I keep doing that 0 or more times. Okay. Suppose this is, I know, I'm sorry. So I'm taking a left-hand side and replacing it by right-hand side. Can it be any old left-hand side, or does there have to be some? It has to be what?
the left-hand side associated with that right-hand side.
True. But what does the left-hand side of these rules have to do with alpha? They have to be equal to. Suppose I'm replacing with A goes to A, B, C. Okay, suppose this is the production. So here's my left-hand side. What can if I apply this, what can I say about alpha? This guy's got to occur in alpha somewhere, right? Otherwise, I can't apply this production, right? Okay. Okay, so I can't just willy-nilly say, oh, look, here's this nice shiny production, let's apply it. It's got to, the left-hand side's got to occur in there somewhere. So now let's suppose that this is integer constant. It's a token. Now what do I have? How many left-hand sides of rules do you see in there? Come on, you guys have good eyes. You can see. Amar sees one left-hand side of a rule. Which one is that? Amr, you're in trouble, man. What? That's a token. I'm trying to figure out what left-hand side you're seeing in there.
So am I.
Okay. He's retracted his confession. So how many left-hand sides do you see? None. It is what it is. Yeah, absolutely. That's a nice Zen statement. So when I apply 0 or more production rules, what can that left-hand side get me? What can integer constant derive? Itself. That's it. Since I can't, since this is just a token, and in fact this generalizes to any sequence of tokens. Just a token, there is no left-hand side of any rule. Therefore, I can't apply any rule to derive it. So the only thing that it derives in 0 steps is itself. Okay, so any token sequence doesn't derive anything else. So if X is a token, now let's apply our intuition here. In this state, I've seen something alpha could derive. I'm looking to see something that the token X followed by beta could derive. Then I happen to see that token X in the input. I say, oh, wow, that's great. I've seen the token X. Now I've seen something that alpha followed by the token X could derive, and I'm looking for beta. Okay, so that works for X as a token or as variable. Okay, questions? All right, and let's look also at the situation where I have A goes to alpha dot X beta. This means I've seen something that alpha could derive, and I'm looking for something that potentially X beta could derive. Suppose X is a non-terminal, but X is a variable. So in this situation, I'm looking for something that X beta could derive. And X is a non-terminal. So let me do an example. Okay, let's do an example. Let me think of what's a reasonable example over here. Suppose I have a state that's labeled as statement goes to while dot expr statement. Okay, so there's my dot over here. So in this case, what this state is saying is that in this state, the parser has seen something that I could derive from here. So it's seen a bunch of other stuff, and it's now recently seen the keyword while, and it's seen a left paren, and that's how far it's gotten. So now, a legal continuation would be to see something that expr could derive, an expression, followed by a right paren, followed by a statement. Okay? In this case, the parser is looking to see something that could be derived from this sequence. Now, if the input actually contains something that expr could derive, followed by right paren, followed by statement, then it must be the case. So now suppose I have some production that says expr goes to expr plus expr. Okay? So if that's the case, and I'm saying over here, hey, I'm waiting to see something that expr could derive, then it must be the case that one possibility is that I might see something that expr plus expr could derive. Or maybe I have expr goes to, sorry if you guys can't see from the back, expr goes to int const. Maybe at this point, I'm looking to see something that int const could derive. So at this point, one possibility would be to see something that captures this. Okay? At this point, I can say, look, because this is a production, I'm waiting for expr. Well, if I'm waiting for expr, then one possibility, not the only one, but one possibility is that I'm waiting for something that a production for expr could get, with the dot all the way on the left. Another possibility might be some other production for expr, dot int const. Another possibility might be dot expr greater than expr, and so on. Okay, for all of the different possible productions for expr. The point is that now I'm looking for something that expr could derive. I don't know which it will be. So I'm looking for something that one of the productions for expr could give me, any one. And I want my automaton to make this transition without actually without me consuming anything in the input. So these are epsilon transitions. Okay, these are transitions that the automaton is making unilaterally on its own. Okay? So if the symbol to the right of the dot is a non-terminal, it's a variable, then for each production x goes to gamma of that non-terminal, this is a possible continuation. Okay? Because the only way I can derive something from x beta is to first derive something from x, and the only way I can do that is through some production involving x. So there's going to be a whole bunch of epsilon productions, one for each production of x. An epsilon production is a non-deterministic transition, which says that the automaton makes this transition without actually looking at the input. Okay? Is that really weird? So this is a non-deterministic automaton, which means that the automaton kind of is in many different states at the same time, and it's processing these in parallel. And which one wins out? Some of them will die, because if it makes the transition that goes, expr plus expr, and the input down the road doesn't have a plus, it has a greater than, then this one will just die away, and this one will keep going. So eventually one of them has to survive. All right? Okay, so questions on this. This is my automaton. Let's do a little example, my palindromes. Oh, I'm sorry, this is not palindromes. This is a bunch of zeros followed by an equal number of ones. So this is the language of balanced parentheses. Okay? Whole bunch of left parentheses followed by a whole bunch of right parentheses, and they balance out. So s goes to 0, s1, or s goes to epsilon. So here are all the possible items and the states of the viable prefix non-deterministic automaton. So let's just quickly walk through this. S prime goes to dot s. So I've augmented my grammar and added the s prime goes to dot s. That's the initial state. From here, because this is a non-terminal to the right of the dot, I have s goes to dot s01 and s goes to dot epsilon. These are the two states with epsilon transitions on them. This is from the last thing that I was talking about, those epsilon transitions there, to go to here or here. Also, here's the dot. So if I see something that s derives, I can transition to s prime goes to s dot. So the dot walks over. All right? This transition is from here. And the other two, the epsilon transitions, were here. Okay, so now from this state, I have a token to the right of the dot. So I don't have any epsilon transitions. But if I see something that 0 can derive, namely 0, then I go to a state where I've seen something that 0 can derive, and I'm looking for something that S1 can derive. So the dot gets walked across. I have a variable to the right of the dot. So that pulls in the epsilon transition things again. And I have an epsilon transition to this guy and an epsilon transition to this guy. Also, if I make a transition on the symbol S, then the dot walks over and I get this state. And from here, this is a token, so I don't have any epsilon transitions. So walk the dot across. If I see a 1, I'm in this state. All right? So one thing that I want to point out is that epsilon is not something that you see in the input. Okay? If you call the parser will never say, oh, I have an epsilon, look. And that's because epsilon is simply a notation that says there's nothing there. That's the empty sequence, right? So the parser will never say, oh, I have the empty sequence. And for that reason, S goes to epsilon always gives you a dot. And you can't, sometimes when people are constructing parse tables, and this is a really common mistake on midterms and such, people are constructing parse tables, they'll say, oh, look, I have a dot to the left of the epsilon. And then if I see an epsilon in the input, I walk the dot across. And of course, you never see an epsilon in the input. And if I have S goes to the empty sequence, that simply translates to an S goes to a dot. There's only one thing over there. There's no position to the right or the left of the empty sequence. OK? So that's the non-deterministic automaton. The whole point of this automaton is to allow us to construct parse tables. Okay? And what the parse table does is it tells us when we can shift and when we can reduce. Quick preview of what's going to be coming. When I'm in a state with an item like this, what that means is that in this state, I'm looking to see something that 0, S1 together could derive. All right? So suppose now the next input token is a 0. What the parser will do is it will say, oh, look, what I'm looking at in the input matches what I'm expecting. But I'm not done, because what I'm expecting is to see something that 0, S1 can derive. At that point, I'm done with this production. If I see S0, then I'm partway to my goal. So what I will do is I will shift that 0 onto my stack and move to this state. All right? So if you think back on the actions of the on the entries in the action tables in certain situations will say shift and go to this state, or push this state on the stack. Same difference. So in a situation like this, the action table might say, here, if you see a 0 in the input, shift and go to this state. Okay? You have a state number. Now, in some situations, in a situation like this, it might say, look, what it means over here is that I have seen something that this production could derive. So in this state, I'm done seeing something that I could derive from using this production. Because I've seen something that 0, S1 can derive. So what I maybe want to do is reduce. So that when I have a dot all the way on the right, that tells the parser that I have a reduce coming up. So the question is, when should I reduce? Do I just reduce willy-nilly whenever, or am I careful about when I reduce? It turns out that that is the key thing. The decision about when to reduce, that's the key thing that distinguishes the various different LR parsing algorithms. Okay? And it'll turn out that in order to figure that out, because that is really the most important thing that we'll be talking about for a while, in order to do that, I'm going to have to digress, make a big old digression to figure out some theory to figure out when we can reduce. Okay, so that's something that won't happen today, but we'll pick up on Wednesday. But here's why. A shift action is pretty unambiguous. Okay, I'm looking to see something that 0s1 can derive. I see a 0. Well, I shift and I move to the next state. No two ways about it. When I'm done, when I've managed to walk my dot all the way across production and the dot is all the way on the right, what that means is that at this state, this guy over here, say, I've seen something that could have been derived from this production. So I need to throw in some reduce actions in some parser states. But if I throw them into too many parser states, I end up with conflicts. Okay, so that's the issue. The reason conflicts arise is that if I have a parser state where some of these items say shift and other items say reduce, that's when a conflict arises. So if I have a parser state with some shift actions because they have things like this, and some reduce actions because they have things like that, and the parser says, oh, I could shift, I could reduce, gosh, I'm confused. That's a shift-reduce conflict. If I have a parser state where I have many different reduce actions possible, then I have a reduce-reduce conflict. That's how conflicts arise. If I'm really, really careful, I could have a state where I have this guy and this guy, but if I don't simultaneously try to shift and reduce, then I'm okay. So what might happen, if I'm really careful and things work out, what might happen is the parse table might say, oh, if you see a 0, then you can shift, and if you see something else, then you can reduce, but you don't have to do the two things on the same input token. Then I'm good, right? Because in a state I might say, well, if the next token is this, I shift. If the next token is something else, I reduce, but I don't have a conflict. Conflict arises if in a state on some given input token, I have to both shift and reduce, and I can't do both. So that's why figuring out what input tokens should correspond to reduce actions, that's what drives the complexity of constructing the parse table. The shift actions are easy. Okay, so that's what we'll be talking about. In order to figure out when I should reduce, we'll look at a couple of criteria. The first criterion is an easy one. The question we'll ask is, okay, I want to reduce, but what tokens could come next? What could show up over here? Because if I can figure out what tokens come next, whatever that means, if I can figure out what comes next, and I see that token, maybe that's a reasonable place to reduce. So we'll discuss that, and that will involve something called computing follow sets. What tokens could follow S? And in order to compute follow sets, it'll turn out we'll have to compute something called first sets. Okay, so we'll just compute some sets. But the real intuition is to figure out what things could come over here where we should be doing reduce actions. So the first criterion, which is the easy one, we'll say, what tokens could reasonably come after an S so that I've seen an S, something derivable from S, and I can do reduce. It turns out that that's not good enough. That still gives us conflicts in some situations. So we'll construct a little bit more elaborate tokens called LR1 tokens. That's when the tokens will have some additional stuff in them. And we'll talk about that stuff a little ways down the road. So are there any questions about the viable prefix automaton? OK, so go ahead, get started on the project, and set yourselves, one second, guys, I still have a couple minutes. Set yourself some internal milestones. You want to get the BNF to YAC translation done fairly soon. This project, this particular assignment is a lot of work, so get started on that soon, OK? See you guys on Wednesday.